All right, guys, so here's a problem that I want to look at with you guys. So you have a particle traveling into a magnetic field. And so this is a mass spectrometer. So like this is something they use a lot in nuclear physics, and they use a lot in chemistry. You want to, it's a way of measuring the mass, like because you can. There's ways to figure out the charge coming in, but let's say we don't know it for now. So you've got this charged particle with a positive charge coming in at some velocity v. So it's going to come in this magnetic field. And so the first thing I do is draw the path of the particle, and we know that in magnetic fields, the path is going to be a circular path. So let's say the particle is going to go and take a semicircular path and head out that way. And we'll put a little arrow and indicate it's going down. So I didn't draw this before because I didn't want to spoil it, but we can also say the path has a radius r that we know, because you can measure. That's one of the points. You know where the particle comes out or where it hits on your sensor, so you can find, so you know where it hit and what the curvature is. So now I've done part A. We've got that. So now I want to find the ratio of charge to mass of the particle. So the way I'm going to do this, I'm going to do it like we started the other one before. So I want that formula that we had, where we said that the magnetic force is equal to QVB, right? And since it's going in a circle, I'm actually going to set that equal to the centripetal force, mv squared over r. And once again, I've got a v on both sides, so I'm going to cancel that. So now, let's just rewrite this real quick as QB. Well, this tells us QB equals mv over r, right? So what are we looking for? We're looking for the charge to mass ratio. So that's going to be, so we are looking for charge over mass, right? So I'm going to solve for that. So I want to get this b to that side, pull the mass over here. So I'm going to say Q over m is equal to v over br, right? And if they gave us numbers, we could put those into a calculator and figure it out. But this charge to mass ratio is really important in identifying particles, because especially once you get to the heavier stuff, you get like the charge to mass ratio are very different. Like for example, hydrogen has a 1 charge and 1 mass, right? So because it's hydrogen, it's got 1 proton. Well, the thing is, okay, so the hydrogen has a mass of 1, a charge of 1, and no neutrons. So its charge to mass ratio is 1, right? But say we wanted to go helium. Well, the mass of helium is 4, because it's got 2 protons and 2 neutrons, so I've got 2 protons and 2 neutrons. So its charge to mass ratio is going to be, well, 1/2. And then if you went to something like uranium-235, something big. So we'll do uranium-235. It's got 92 protons. I don't know how many neutrons it has off the top of my head because I don't want to do the math. So its charge to mass ratio is going to be, of course, 92 over 235. So it's getting even smaller. So it's not entirely unique, but it's a really helpful tool in identifying what element is. But I guess I've digressed. That's gone a little bit too far. But it's still useful information to have. All right, so part B, we've got that done. What is the work done by the field in part C? So let's call this guy part B, and let's do part C right here real quick. What is the work done by the field? Well, we said earlier that magnetic fields, when you're in circular motion, actually don't do any work. So it's just going to be something you have to remember. So in this case, I can say, just pretty much write down work equals 0. Done. And then part D, it wants to know, does the velocity of the particle change? So I don't remember if I said it correctly in the last video. But one thing we need to know is that the velocity does change, because velocity has magnitude and direction. So the direction is going to be what's changing because the velocity is a vector, right? So it's got magnitude, direction. Okay. So its magnitude, right, is speed. So its speed isn't changing because its kinetic energy is not changing because you're not doing any work. So this guy is constant, but its direction, it was going this way, right? Its velocity is here. Now it's going that way. So the direction's definitely changed. So my velocity's changed. So yes, the velocity of the particle changes. Now another way they often ask this question is like, is it accelerating, right? You could say, is it accelerating? Because that's the same thing. And of course it's accelerating. Its circular motion is always accelerating towards the center. All right, so that's that problem. I hope you enjoyed it, guys. If you did, like and subscribe and hit that bell button for if you want notifications. All right, see you later.